Good morning, everyone, and welcome to a day full of press conferences. The first one is on greatest hits, water in social media, smartphones, GPS, and popular music. I'd like to remind you that the floor will be open for questions following short presentations by each speaker. When asking questions, please say your name and affiliation and who the question is for. Journalists watching remotely can ask questions using the chat and the live stream page. And if you want any documents, such as press releases, presentation slides, etc., relating to each press conference, please go to media.egu.eu/documents. Taking part in this press conference, we have Dirk Eilander, who is a junior researcher and consultant at Deltares in the Netherlands, Salvador Pena-Aro, who is an hydraulic and environmental engineer at Fotrac AG in Zurich, Christine Larsen, who is a professor at the Department of Aerospace Engineering Sciences at the University of Colorado in the US, and Karen Aplin, who is a physicist at the physics department at Oxford University in the UK. And now you can start, Dirk. Thanks.
Thank you, Barbara. Welcome, everyone. I'd like to present innovative research today done by Flattex and Deltares with the title Twitter as a Basis for Real-Time Flood Extent Maps. My name is Dirk Eilander. I work as a hydrologist at Deltares. And I've done this work together with two colleagues, Arne-Jan van Loenen and Ruud Roskamp, and our partner at Flattex, Jurjen Wagemaker. Let me start with a question to you. Who of you is actually using Twitter? Most of you are. In this presentation, I will show you how your tweets can help emergency services during floods. Let me start with this example from Jakarta. In Jakarta, also referred to as the Twitter capital of the world, we measured up to 900 tweets per minute during floods earlier this year. And these tweets tend to have a very detailed description. There are not only pictures, as you can see on the monitor, but also very precise indications of where the observation was made, and sometimes even a water depth, as you can see in the top right picture, where it mentions a street and a water depth of 35 centimeters. Furthermore, in Jakarta, we face frequent floods, but we know very little about the extent and the impact of these floods, especially real time when they are happening. So our method focuses on using this new big source of information and translate this into information for emergency services. In the next few minutes, I will present the method and come back to the same example with some results. So the first step in the method is to mine data from Twitter. We do this based on textual information. So every tweet which has a mention of floods in Bahasa, Indonesia, and that's the word banjir, we mine from Twitter. Then we apply a spam filter, we apply another filter to get rid of the retweets. And we analyze the tweets for water depth and location. A location in this case is the exact match of the name of the district. So we know in which district of, in this case, Jakarta, the tweet was posted. Then in the next step, we convert this information to flood extent maps. We do that based on a digital elevation model, which we first have to make hydrodynamic correct. And then we analyze the DEM to find the local depressions. Those are low-lying areas, which are likely to have water ponding during heavy rainfall. Then the tweets from the previous step come in, so we have information per district on the number of tweets as well as on the water depth per tweet. And we analyze for each tweet how likely they are. We do that based on a larger group of tweets to get rid of the outliers, to know which messages are reliable. And we combine this information to come up with flood probability maps. These maps will show you how likely it is that a flood is occurring at a specific time at a specific place. So to come back to this example of Jakarta, you see here the map of Jakarta. The left map shows you the number of tweets with a water depth in Jakarta during floods earlier this year on the 10th of February 2015. And the darker color indicates more tweets. So this is the result of the data mining, basically. Then we use this as input for the next step to come up with these flood probability maps. So in this map, you can see that the dark colors are the places where there are likely floods happening at this moment. And you can see that in the center of Jakarta and in the northern parts, in the center along the river, but also in the northern parts, some floods are occurring. We have validated these maps with ground truth photographs from the floods, and found that in 67% of the districts and in 68% of these points, there were over 100, we modeled the flood correctly. So although there's still some room for improvement, these maps are very useful information for emergency services to, for example, find the people who are affected or to plan for evacuation routes. But also in not only during the disaster, but also in the prevention and preparedness phase, this type of information could be useful. For example, to find areas which are flood prone or to validate hydrodynamic models. And also in the step after, in the phase after the disaster, this information could be used to have a quick assessment of the flood impact. This is, for example, useful information to speed up the recovery. So for my presentation, I also like to refer to my poster this afternoon and at the red floor. Thank you for your attention.
Well, good morning. My name is Salvador Peña. I work at Fotrac. We're a small company based in Switzerland. And we specialize in flow measurements and particle tracking. And we have developed an app for measuring the river discharge. First, I'm going to show a short video on how the process is done. Could you click on the image, please?
Oh, on the image.
So the idea first is to take, just with the mobile, I can take a movie, 5 seconds of a movie. The mobile can be a bit shaky, so first I have to stabilize the image. All this is done inside of the mobile. When it's stabilized, I get some reference points to do some camera calibration, and now how the camera is looking to the river. And then I map the river geometry to the image. And with that, I can look for the water level. So the next step, once I have the water level, is to calculate the velocity. And the surface velocity is calculated comparing some consecutive images that were taken with the movie. And here I'm just showing the results of the analysis of the surface velocity. And you can see how these virtual markers are moved with the flow velocity. So then I can, with the surface velocity, we calculate the velocity in the vertical dimension. And with that velocity in the vertical, and we have the water level, we can, and the geometry, then we can integrate and get the discharge along in the river. Can be in a river, can be in a small channel, irrigation channel, can be applied in different places. And everything is done inside of the smartphone. So there are some advantages in the smartphone. First, of course, I have a camera, I have a gyroscope, so I can get the position where the mobile is looking, and it helps me to get the calibration of the camera. Then also I get the coordinates of the location, and then after the process is done, I send the data. I can send it by an SMS, or if I have a connection to internet, I can send, beside the information of the discharge, I can send the movie to a central. The only things that are needed is I have to know 4 points, that I have to know the relative position between them and the channel geometry. And this information is introduced directly in the mobile. These are some screenshots of the app. Once I introduce that information, I can just start recording a movie. It's just 5 seconds of the movie. Then the app calculates the water height, or even I can adjust it manually. And then starts doing the processing of the surface velocity and the discharge. And all this is done inside of the mobile. These calculations takes around 40 seconds, but I don't need any external aid. And then after the calculations are done, these are sent by SMS. and then directly can be collected in a central and can be published, no, in a web, for example. We have tested this method in different situations, like normal rivers with normal flow, also in some channels with slow flow, with faster flow, rivers with very low flow, and it works fine. Still, the app still kind of in a beta version. And we have two different ways to process, as I said, that everything is done inside of the app, but also I can send the video that I took with some information about the position, and then I can process that after in a PC, so I can do more detailed analysis. Also, one of the advantages is that I can take the mobile wherever, no? And the only thing that I need to have is to have a clear view of the river. But if there is, again, a higher event, I can just go there and take a movie, and then I can process it. So we believe that with this, we can collect more data because it's really easy to use. And by collecting more data, not just in rivers, but also in irrigation channels, that can improve to get more data and can improve water management. And also, as mentioned, can be also used in floods. We intended this app to be used by water or community agencies. And currently, it's being used by the Environmental Agency in Switzerland and also by the Swiss Cooperation Agency, and it's being used in Tanzania. So, as I said, one of the biggest advantages, I think, is just very easy to use. I don't need anything, it's not intrusive, it's just a video that is taken from some distance. And it's with a mobile, you know, that now many people have a mobile. Thank you.
Okay. I have a PowerPoint water, Larson, that one. Yes. Thank you. Thank you. Okay. So I'm going to talk about using GPS receivers to measure snow. It's not the first thing I started working on. I'm just going to outline a little bit why most people use GPS. Probably 99% of people use GPS now in their phone, as well as their cars. But there's also a lot of people that use GPS for fleet tracking, for example, businesses. It's the preeminent way to determine time. Even though you think your cell phone's telling you time, GPS told your cell phone first. So it's the way that our infrastructure works. It's also extremely important for professional surveying and for farming and construction. So both of those industries also use GPS quite a bit. And people here at this meeting, those of you who've been to EGU before, know that it's something that's used to measure how the ground deforms. For example, on the left-hand side here, I'm just showing an inset of how the ground deforms in Southern California because the San Andreas Fault, as shown on the right-hand side, is splitting the state of California. So on the left-hand side of that plot shows you that offshore it's moving 47 millimeters per year relative to sort of a region in the desert. And it's that deformation signal that causes earthquakes in California. So the way you're using GPS in your phone and the way I use GPS for most of my research is that we're measuring distances to satellites. And from that, we calculate latitude and longitude and height. And then your iPhone or your smartphone will then put you on a map. That's how we all tend to use GPS. But about 7 or 8 years ago, I thought about using the reflected signal to do something different. So instead of calculating latitude, longitude, and height, I just said, well, what can I do about the signals that are bouncing off the surface of the Earth and arriving at my, in this case, antenna, which is shown here in that dome. What can I use those bounce signals for? Because the bounces should tell you something about the surface. The bounces don't tell you where you are. That's what you use your regular GPS phone for. But these bounces should be able to tell you whether the ground is wet, whether there's snow on the ground, or whether there's vegetation on the ground. So I've been using these signal bounces, which arrive late, to determine these things. I don't have a lot of examples. I'll just show you one or two. On the right-hand side, you'll see that's actually a GPS antenna, that little white disc there. And then there's a pole that has black and white markings on it. That pole with the black and white markings, that's how they normally measure snow. They send people out, they send field crews out to measure how high the snow is. So they send out a field crew maybe every couple of weeks. If you'll see the little inset, you'll see that the snow is within about 20 or 30 centimeters of the top of the GPS antenna. So there was almost 2.5 meters of snow that had fallen since that photo was taken in the fall before the snow fell. So what's shown on top is just a representation of some results I've had for the last, I guess that's 6 years, comparing the pole measurements in the red triangles with this new method using GPS to measure snow. So we can also use this, like I say here, to measure soil moisture and how much water is in the vegetation. And the same method can be used to measure sea level. I think I have a movie, and I shall attempt to show it, and it seems to work. We were validating the method by taking a photograph of a pole that was off to the side, so we just decided to put it together. So the blue dots down below are just me using the GPS data to measure snow depth. The same GPS data are used to measure, in this case, the inflation of the Yellowstone caldera. You could also use it in the Sierra Nevadas or any mountain site where there's snow. You could use it to measure snow depth. And then I wanted to highlight, since I was here at the EGU, that while this initiative I've been working on is in the Western US, that's just because my funding comes from American agencies, and I wanted to emphasize there's a large number of GPS sites in Europe that could be used for the same technique. This on the right is just a plot I found online of a large network called EUREF. On the left, I just wanted to highlight that GPS is not the only satellite navigation system in town. That Europe has one, Russia has one, and the Chinese are also building one. We can use all these signals to do environmental sensing for soil moisture, snow depth, sea level, if we're close enough to the coast, and vegetation water content. So the take-home message, we can do this. The receivers were installed by other people to do other things, in particular by land surveyors and geoscientists. People would use these data, people being scientists primarily, climate scientists, engineers that validate satellites like ESA's SMOS, but also the US SMAP mission, which was just launched in January. It could also be used for mitigating and predicting flooding, and as well as with drought. And I would just point out that most of the people that install these networks consider them to be a public good. The scientists consider them to be a public good as well as the surveyors, and so they provide the data to the public for free. So essentially you have a snow and soil moisture network for free. And I'll speak a little bit more about this tomorrow in my presentation on Wednesday. Yeah. Just ignore it.
Okay, so this is something a little bit different that doesn't use any smartphones or GPSs. This is reporting some work that I did with my colleagues on looking at popular music and how it's influenced by meteorology. So our initial motivation for this work was that scientists often assume that weather is reflected in popular culture just because people are influenced by the natural environment. And this is very much an assumption that we make. Obviously it's important, but we wanted to test this kind of sensibly for music using a scientific approach. My colleague Paul Williams and I previously did this for classical music, and it was quite successful and people were very interested, but we thought it would be better actually to do it for pop music because pop music's more accessible and many more people listen to pop music. Pretty much everyone knows pop music songs, so we thought this was a good way to investigate how popular culture was influenced by the natural environment. So we found that there are about, so we counted up all the songs, the pop songs, and we also used some databases to try and find pop songs that were influenced by the weather. And we found there were about 900 singers or songwriters which were associated with weather-related songs. And we also found that many pop bands had names that were related to the weather. And you can see around the outside some examples. And in the weather-related names, we found that sun and warmth were the most popular themes, although you can see that they're not all about sun and warmth. Coldplay and Wet, 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 for example, are some nice ideas. We found that the most popular weather to be pictured in pop songs were sun and also rain. And they made up about a third of all the weather references we found in the 900 songs. And if you also look at pop songs that portray multiple types of weather, we found that rain and sun were most popular to picture together. So they're definitely the ways in which weather is depicted in popular music the most. So we found that the major way weather was represented in music, in pop music, was through the lyrics. This wasn't exclusive. We did find that the music pictured the weather as well, but the lyrics were the most clear way. And we found that words were able to link the weather to certain emotions, and this is why it's quite a powerful way to communicate. For example, love and relationships, which are the topics of many pop songs. We found the sun almost always was pictured positively. The rain references were more mixed. I suppose that's what you might expect. So there are some examples below of the sun being good and the rain being bad. When you're smiling, the whole world smiles with you. And when you're happy, the sun comes through. But when you're crying, you bring on the rain. But that's not exclusively the case. So some people like the rain. This I love a rainy night. The rain is pictured as washing all the cares away. And then sometimes the sun is pictured negatively in this sort of slightly sadder song below about why does the sun go on shining. So we found that some songwriters were particularly influenced by the weather, particularly the Beatles and Bob Dylan. I think Bob Dylan was the person who was influenced most of all by the weather. About a quarter of all his songs were about the weather. But the Beatles were also very keen on writing about the weather. Lennon, McCartney and George Harrison all wrote about the weather. And they were influenced by the weather. So Here Comes the Sun was written by George Harrison in April '69, and it was the sunniest April for many years, 189 hours of sunshine that year. And it wasn't that sunny again for about another 30 years. So there's evidence that songwriters were influenced by the weather. So we think this is the first quantitative study assessing weather in pop music, so we're the first people to sort of count up the different types of weather. We found that in classical music, meteorology was an important inspiration, and in pop music, so this is pointing to the sort of generality of the influence on us. But the outcomes were quite different, and there are some differences in our study, which I've put in a table that you can see. So we found that in pop music, weather was mainly in the lyrics, whereas in classical music, they're mainly sort of copying the sounds of the weather. In pop songs, weather was used to reflect emotions, whereas in classical music, it was much more literal, about a storm or something like that, rather than being about somebody's relationship breaking up and then feeling down. In popular music, it was the sun that was most popular to picture, but in classical music, it was storms. And we found also that songwriters, in the sort of evidence we found, songwriters were influenced by sort of specific sunny days, that type of thing, or specific weather events, so storms or hurricanes. Whereas in classical music, it was kind of more like an average of the sort of climate that the composers lived in. So we found that weather in pop music is used to emotionally connect the listener to their environment. And weather, of course, is the most accessible aspect of the natural world, and we found that we think weather is a kind of backdrop or maybe a sort of soundtrack to life, and so its day-to-day variability is a good way to convey human stories and also to get people to think about the ups and downs of the weather as a parallel to perhaps their lives, and in this way it gets people to think about science and the natural world who might not necessarily be interested in it at all. We found, finally, that pop music actually tends to depict weather using metaphor. So it's an accessible style of music, but the weather is reflected in a sort of sophisticated way, whereas classical music is perhaps a bit more difficult to listen to, but is much more literal in how it depicts weather. So pop music is a bit more sophisticated in its using this sort of soundtrack to life. So that's it. I'm giving a talk on Friday morning at 10:45, and we also have a paper which is going to be published in Weather next month. I'm afraid the paper's not out yet, so you'll have to rely on what I say for it. Okay, that's it. Thank you.
Thank you very much for your incredibly interesting and clear presentations. We'll now open the floor for questions. Does anyone have any questions for the speakers?
Hi, I'm Liz Gallagher from Environmental Research Web. I've got a question for Christina. What is it about the reflected signal that gives you information?
You can think of the reflected signals being like an interferometer, like you learned about in high school intro college physics. So there's an extra distance that it travels, and that extra distance that the reflected signal travels interferes with the direct signal. So you have your normal direct signal and you have this reflected one, and they're going to interfere. And if we had geostationary satellites, if GPS satellites never moved, we'd have nothing. But since GPS satellites rise and set, that allows the interference pattern to change with time. So what I use the interference pattern for is a couple things. If the layer that reflects moves up and down like it would if snow's going up or down, the frequency of the interferometer changes. So that's kind of nice. I just look at the frequency of the interference pattern. If there's a lot of wet vegetation in my signal, that attenuates it. So I look at the amplitude of the interference pattern. And for soil moisture, when the ground is wet, the surface geometry stays the same, but the signal penetrates a tiny little bit extra, depending on whether it's wet or dry. And so there I just look at the phase of the interference pattern because it's a very small thing. So I'm not sure if that quite explained it all, but those are the things that we use, the amplitude, the phase, and the frequency of the interference between the two to retrieve those three things. And the same for sea level, it's the same as snow. As the ocean goes up and down, that changes the reflection height of the surface, and I use the frequency to retrieve that.
Thank you. Are there any additional questions? No? Okay. Wait.
Michael Jensen, freelancer in Austria. I have a question to Dick Erlander. I could see the two maps with the flood risk and with the response in Twitter. There was a discrepancy because there was on the flood risk map was a very red spot at the upper right end of the map, and there was no response in Twitter. Is this because of the density of population, or how can you account for this?
Yeah, thank you for your question. So basically, what we do is we analyze this big amount of tweets, and we come up with the most reliable. So what happens a little bit in the top right corner is also a little bit biased because we have the tweets on a district level. In this district is really, really large, so we don't really know where the tweet is likely to be. So there were a few tweets in this district, and we found those reliable, so that's why a large red area came up because of the large district. So it's in this map, it seems like that's the most, the part with the most risk, but it's as risky as other smaller red areas, to put it that way. Does that answer your question?
Yes, okay.
Are there any additional questions? Okay, if not, you are welcome to approach our speakers now. And if you want to book rooms for interviews, you just go to the info desk here at the press center. And the next press conference is coming up at 11 on water signatures on the Martian surface. Thank you all very much for coming. Thank you very much for your talks.
Thank you.